D-star Lite is an optimal pathfinding algorithm that works backwards from the goal to the start. Like dynamic A-star, it can also account for changes in the graph without recalculating the entire graph from scratch. Today, I'd like to show D-star Lite working with a graph of vector 3 positions in the world, but we're going to use C# generics to create an implementation that can work with any type, including complex ones. Custom types will just need to calculate their own costs, heuristics, and deal with the results as appropriate. Let's get right into it. Let's have a quick walk through a diagram. I'm going to make a start node A and a goal node E, and then I'm going to make a whole bunch of nodes in between. So we'll have a B, C, and what else? D, and then let's also make an F. Now, D-star Lite is unique because we work backwards from the goal to find a path all the way to the start. Every node in this graph is going to have costs associated with it. The first one is called the G cost, and that's the actual cost from the goal to that particular node. And then we have a right-hand side value, and that is actually the estimated cost, like a best guess through the predecessor of what we think it's going to be. So the goal, of course, is going to be 0 because it costs us nothing to move to the goal. For every other node in the graph, it's going to start at infinity because we haven't calculated any values for them yet. The first step will be to find all the nodes that connect to the goal and estimate their right-hand side value. In this graph, that's only node D, and since it's only one step away and we're assuming the cost between nodes in this little example here is 1, it gets a value of 1 in the right-hand side, and that's step 1 complete. Step 2 is to say, okay, let's confirm that the cost of D is 1, and then let's guesstimate the cost of traveling to its adjacent nodes, which is F and B. So we'll give those a value of 2 on the right-hand side. Step 3 will be to confirm F and B have the correct costs, and then check their adjacent nodes, which right now F is a dead end, but B connects to C and A. So those get 3 on the right-hand side. And then the final step in this small example is just to confirm that A and C have the correct costs, but we've reached the start node, so we know that we're complete. Now, in this simple example, we can only see the traversal, but what happens during the algorithm calculation is that each of these nodes is given a special key. The key determines its priority and how it gets processed and is based largely on the cost of getting there. So we're going to process nodes that have lower value keys first. With the lower value key, we're guaranteed to always find the optimal solution. Now, some nodes turn into dead ends, and we just process another node. And eventually, when we finally reach the start node, and we're able to say, yes, the start node has a value, we know we have found a complete path, and not just that, but an optimal path to get to the start node from the goal node. All right, I'm going to be using a lot of floating point numbers today, so I'm going to add an extension method here to judge the equality of two floating point numbers. Like most pathfinding algorithms or any sort of graph traversal, we're going to be working with nodes. So I'm going to make a node of any type T so that we can handle anything in the future. We can keep a reference to our type T as data. Now, like most pathfinding algorithms, we're going to need to be able to calculate a cost and a heuristic for each node. So I'm going to keep these methods with each node in case they have to be different for each node in more complex scenarios. In today's example, because we're using vector 3s, this will almost always be the same, the distance between one node and another node. The little yellow squiggly line there made me think of something I wanted to show, and that's these little crayons down in the bottom right corner. If you're using Rider and you don't like all the code hints and the style inspections and stuff, you can come down here, click that, and you can start hitting the slider or using these toggles to quickly make adjustments to that. Anyway, I'm going to leave it and keep going. So in addition to these two methods that we're going to be using, we also need to keep track of this node's G cost, which is the cost of this node to get to the goal. And we're also going to keep track of the right-hand side. The right-hand side is the minimum cost known from this node to its neighbors, plus the cost to reach those neighbors. With vector 2 or vector 3 types, after calculation, the goal and the right-hand side will almost always be the same. And to make this convenient, let's have another property here that just will tell us right away, is the value of the goal approximately equal to the right-hand side? Now let's come down a little bit because every node will need to know about its neighbor nodes. So we'll keep that as a list. And with that out of the way, we can add a constructor here. We'll set those values. And then on top of that, we're also going to set the G cost and the right-hand side to be float max value, meaning the algorithm hasn't calculated the correct values yet. Just going to add a few comments up at the properties here, just in case somebody's looking at this later and isn't sure what this means. Okay, now I'm going to collapse this node class up because we're done with it, and we can move on to the algorithm. The D*Lite algorithm is going to want to know its start node and its goal node, and also all of the nodes. On top of this, we're going to keep another value called a key modifier, and this value gets incremented anytime there's a change in the graph so that we calculate new keys and things in the priority queue will get readjusted. Now, we don't have access to .NET's priority queue, but we can make a sorted set. Now, sorted sets are very fast to add or remove items and to get the lowest cost item. What they're not very good at is actually finding something in it. So what we're also going to do is keep a dictionary that we'll call lookups. So if I know what a node is, but I want to look up its key so that I can quickly find it in the sorted set, we'll be able to grab it from there. Maintaining two collections like this isn't really ideal. And so somewhere down the road, we should actually migrate this into a new data structure that we could actually call priority queue. So the sorted set will keep all of our nodes in order by their keys, but working with this tuple of two floats as the key isn't really ideal. Why don't we make another data structure just to hold keys, really? So wherever we were using the two float tuple down below, let's just replace that with key. Then back up in the key data structure, we can just have two floats here. We call them K1 and K2. Those can just come in through the constructor, and then we don't need anything too fancy here, but why don't we overload all operators? So let's overload the greater than and less than operator. For those, we're going to use the primary key as the main judge, but if those are approximately the same, we'll use the secondary key. Now, we'll do something very similar with the equals and not equals, but not equals can just be the inverse of equals. Now, for completeness, let's add equals, get hash code, and let's also override toString, just in case we want it for debugging. That's really all we have to do with the key class, so I'm also going to collapse that up so it's out of the way, and then let's continue with our algorithm. So a sorted set class needs some kind of comparer, otherwise it's just going to use the default. So now that we have some functionality in our key struct, we can actually create a little comparer to pass into the sorted set. So here, what we want to do is actually compare keys. So we'll say, when we're comparing two items from the set, if the first key is less than the second key, return -1. If it's greater than the second key, return 1. Otherwise, return 0. And that's how a sorted set keeps things in a proper order. Then we just pass that in through the constructor of the sorted set. Okay, we still need a constructor for our D*Lite class. And there's not too much to pass in, just our start node, our goal node, and of course our list of all nodes, which is our graph. Okay, we can start implementing those algorithm methods now, and we want to start with initialize. So the first thing in initialize is make sure that our two data structures are empty, because anything inside of those is going to be calculated again. So when we're starting the process, let's make sure it's empty. Then on top of that, we also want to make sure that our KM value is 0, because when we run the initialize, it means we're running for the very first time. Now, it's possible that we've run this algorithm once already and we're just starting over fresh. So let's make sure that every single node has a G and right-hand side of float max value. In this algorithm, the goal will always start with a right-hand side of 0. And because it's the first node that's going to go into our data structures, we also need to create a key for it. So we're going to have to write a method called calculateKey. Once we have that, we can add the key and the goal node into our data structures so they can be processed. CalculateKey is really a one-liner, almost, except we're actually creating two keys, remember? So the first one, slightly more complex, and is going to be the primary. I'm just going to break this onto 2 lines so it's easier to read. The first key is going to take the lower of either the G or the right-hand side score, plus calculate the heuristic between this node and the start node, plus add that KM value. The second key will just be either the lowest of the node G or the node right-hand side. Remember that KM is going to get bumped a little bit every time we make a change to the graph. So if we ever have to calculate a new key for a node, it will always be different than the key it used to have. So the basic idea of this is the closer that a node is to the goal, the lower the value of its key. That means when we're processing all the nodes, things that are closer to the goal node are going to get processed first. Next, let's get into the update vertex method. This is actually the method that gets called a lot, and it looks very simple there in the algorithm. First, let's calculate a new key for this node because we're potentially going to be processing it again. Now, we've got 3 logical branches to go through here. The first one is, what happens if we haven't processed this node to its optimal cost yet? Meaning that G is not equal to the right-hand side, and we don't have it in our data structures yet. If that's the case, we just have to add it. That'll make sure it gets processed the next time we run the main part of the algorithm. The next branch is kind of the opposite. That means we have already optimized this node because G is equal to the right-hand side, but it's still in our lookups. Let's remove it from both data structures. We don't need to process this one anymore. The last branch is for when the node is in the lookups dictionary, but its G and right-hand side values are not equal. So this scenario would come up if the node was already in the lookups, but a shorter path has just been found, which makes G and the right-hand side unequal. So the node in the open set and the lookups will have to be updated with a new key. Okay, let's get into the compute shortest path method. Now, this looks like a lot's going on, but it's actually pretty straightforward. In fact, it's just a giant while loop that's going to process everything in the open set. I'll just get that off the screen, but I'll have a link to the original paper and the full algorithm in the description. This while loop is the heart of the entire algorithm, and it's going to keep running as long as the open set has elements, and either the smallest key in open set is less than the calculated key of the start node, or the start node right-hand side is greater than the start node G. If either of those conditions are true, it means there's still potential to find a more optimal path. Now, because this is a while loop and there is potential to be actually no path, why don't we set a limit on this? I'll just come out of here and make a constant, let's say 1,000 rounds through here. If we get to 1,000 rounds through this while loop, we should just break out because that means there's probably not a path. So why don't we make that the first condition inside of here? If our max steps, which will decrement every iteration here, is actually less than or equal to 0, then let's just give a notice and we'll get out of here. It's possible that there is no path until some of the nodes change. And when that happens, this will get run again on any nodes that we've added back into the open set. So let's evaluate whatever's in the minimum position of our open set. We'll pull that out and put it into a variable called smallest. And then we'll actually make sure that we've removed it from the open set. Remember that open set holds a key and a node together. So the node is part 2 of that variable, and we can get it by referencing item 2. Likewise, we can get the key by referencing item 1. I'll just scroll down and give a little bit more room here before we continue. Next, we have 3 nested condition checks on this particular node. I think I'll just write them out quickly here. So the first one is, what are we going to do if the key is somehow different than when we first put it in the open set? And the second one is, what do we do if the G cost is greater than the right-hand side? And if it makes it past those 2 checks, we'll run through the third part on every node that comes in here. Let's talk about the first condition. So if we have a new key value for this particular node, that means that it is somehow changed since we put it into the open set. So we really just need to get it back in there with the new key, and we'll process it on the next round. In the second condition here, if the G cost is ever greater than the right-hand side, it means that we've actually found a more optimal path. And so we should update the cost of the node to be that optimal value. Next, we're going to have to iterate over all of the predecessors of this node because they're going to need their right-hand side values updated now that the cost of this node has changed. So what we can do actually is make a couple helper methods, I think, for predecessors and successors. So nodes that come before this one and nodes that come after. Now, in a general graph that's bidirectional, that would technically be all of the nodes' neighbors in both cases. But I'm just going to put some examples in comments here. So for example, you might want predecessors are all nodes where their neighbors are this one. And that would work well too. And it really depends on your type T and what you're doing and the directions of your graph. Like, do all neighbors know about each other or some one way? You'll have to tailor these to your scenario. For now, let's just assume it's all neighbors in both cases. So let's come back up to the loop now, where we're going to reset the right-hand side of all the neighbors. Now, we're never going to reset the right-hand side of the goal node. It's always 0. But if it's another node, we're just going to run this little method on it. So we'll get the minimum of either the existing right-hand side, or we're going to run the cost method and try to figure out what the actual cost is between the node and the neighbor. And then we'll add the node's G value to that. Whichever one of those is lower becomes our new right-hand side. And then we're going to process this neighbor through the update vertex method. This means it'll likely get a new key and go back into the open set for more processing. So the final else statement is a scenario when there is no better path found for this node. If that's the case, first let's grab that old G value, because we're going to need it in a minute, but we're going to set the G cost to float.max value, which means this node really isn't worth traversing. There's no path here. However, because we've changed the G cost, what we should do is go to all of the predecessors, and we should include this node as well, and we should make sure that their right-hand side values are up to date. So to do that, we can do some quick math and figure out if any of those nodes had their right-hand side approximately the same as the cost of traveling to the node that we've just modified, then let's just set them to be a very high number again, as long as they're not the goal node. This effectively invalidates any of the calculations that were made on the previous G cost of node, because node is now a very high value too. But while we're here, we also have to go through any of the successors of this particular neighbor, because we want to know if there's an S prime such that we could calculate a better path. So this is like saying the neighbor that was dependent on the original node we were evaluating can now look for an alternate path. If it can't find one, then the right-hand side will stay at float.maxValue, and then it goes back into update vertex for processing. More than likely, it's going back into the open set. So that's it. The while loop will keep iterating until either the open set is empty and we haven't found a path, or it has found a current path all the way to the start and all of the nodes are optimal. If we make it all the way out of the while loop, we're going to set the G cost of the start node equal to its right-hand side. Remember that we set all the nodes' right-hand side to be infinity. So if this comes out as infinity, it means we didn't find a path to the start node at all. But if we have a real number, it means there's a real path all the way from the goal to the start node, at least one path. So that's the bulk of the D-star Lite algorithm, and I hope that made sense. I hope I explained it well. I do want to show one more thing, and that is how do we optimally make adjustments to the graph while it's already computed? In the beginning, I said that was one of the advantages of this algorithm. It's going to vary between games and what you're doing with this algorithm, but I'm going to show you what I've done for this demo, so it gives you an idea of what you could do. So I'm going to call this method recalculate node. It's actually pretty straightforward. Suppose I've changed a node in my game, like I've moved it around, or I've changed its cost to be something extremely high so it's intraversable. Recall from earlier that I said we had to increment the KM value to ensure that we have new keys when we do this. Now, potentially every node that connects to this node could affect things. So let's get all the successors and all the predecessors into a list, and let's iterate over them. And then we're going to do a calculation similar to what we did before. We're just going to set its right-hand side equal to the minimum of what's there now, or we'll run the cost function on it. Each of those neighbors is going back into the update vertex method, and we're going to put this actual node that was originally sent into that method as well. And then we're going to run the compute shortest path method. This means potentially any of those nodes will be recalculated for new values, and they might have a little bit of a ripple effect, but you don't have to calculate the entire graph all over again. That's one of the ways that makes D-star Lite much more efficient. Just before we go into demo mode, I noticed one mistake that I made, and that is here where I removed the smallest from the open set. I failed to remove it from the lookups. Another good reason for us to migrate both of these data structures into one data structure that we could just call priority queue. In fact, I'm going to make that a to-do right now, and I'm just going to jump up to the very top of the class, and there we go. To-do, move to custom priority queue. So now for this demo, I'm just going to make a bunch of waypoints, and I'm going to generate them at random, and I'm going to create random neighbor connections. And then we'll see, not everyone is going to generate a full path, but most of them will, because I'm giving 3 neighbors to every node. All right, I'm just going to put this up on the screen here. We're not going to get into this in too much detail because everybody's implementation is different. And this is just some silly node generation just to test this out. All it does is make a bunch of nodes, connects them all together, make sure that the start and the goal aren't directly connected to each other, and then it just fires up the D-star Lite algorithm, initializes it, calculates everything, and then I've made a little get path method. It's just a greedy algorithm that just grabs the cheapest route from the start to the goal based on all the calculations that we just did, and then I'll make a visual. So let's have a look. All right, I've fired it up and we've got our first path here. So let's take a look. The red orb here is the start, and you can see that it's got a G cost, which means we did indeed find a path. And if we look through here, we can see that a lot of other nodes have their paths calculated, but it's chosen through just my greedy get path method to find a quick way to get all the way to the goal node. Even that's not optimal because we could minimize some hops, but that's a project for further refinement. Let me turn off the environment here actually so we can have a better look at what's happening, and we can generate a few more. In fact, it would be nice to generate one where it can't find the path and see what happens. So here's kind of a longer one. That looks pretty good. Yeah, nice and direct to this one. No surprises on most of these, it looks like. Yeah, I mean, it's definitely fast. That one's a little bit of a detour. Okay, here's one that didn't work. You can tell because the start node has a G cost of infinity. The main reason I'm interested in this algorithm is because I want to use it for GOP. And that's because this algorithm specifically works backwards from a goal, which I want. And also it can be updated at minimal cost. Agent states, and they can be represented just the same as we are representing vector 3s here, and they have a cost to execute them. So moving from one action to another in a chain of actions in a GOP system isn't really that much different than here where we're moving between nodes. They still have a cost. It can all be calculated. All right, that's all I've got time for today, so I'm going to wrap it up. But let me know in the comments if you want to see more about this in the future, or if you'd like to see a different algorithm or something else entirely. And I'll see you there.